Okay, it's 2:02 now. I think we can get started. So hello and welcome to AR6 seminar series. I'm John, the seminar coordinator. Together with me is Miss Kathy Melanie. Kathy is our communication specialist, and she and I will be today's moderator. Today, our associate director, Prof. Ferrero, also joined us, and he will be introducing the speaker. Just so you know that the seminar is being recorded. We will put the video recording on our YouTube channels. Please feel free to check out, and you can bring up questions after the speaker's presentation. And today we are excited to have the speaker together with his new book. And Kathy, I will let you introduce something about the new book.
Yeah, so today our speaker and his publisher have very generously decided to give away a copy of his new book. It's called The Climate Demon, Past, Present, and Future of Climate Prediction. It's about climate predictions and the computer models behind them and how they play a key role in shaping public opinion in our response to the climate crisis. If you want to win this book, we'll have a bit of a raffle. There is a Google form link. It's in the chat right now. If you go to it, you just have to put in your name. It should be the same name that you have joined the WebEx with. And at the end of the seminar, I'm going to announce a random winner who will receive the book. It takes about a minute. So thank you, everyone. Okay, I'll turn it over to Ralph to introduce the speaker.
Okay, yeah, thanks, John and Kazi. Yeah, I have the pleasure of introducing our speaker, Professor Saravanan, who's the also the department chair at atmospheric sciences at Texas A&M, and he's a world-renowned climate specialist, and he has served on the NRC committee on the interseasonal interannual climate predictability. He's also on the science steering committee of the Parada buoys in the Atlantic Ocean. And he's going to talk to us today about unprecedented climate. I think we'll learn a bit about what's precedented and what's unprecedented. And so turn it over to our speaker and look forward to his talk.
Okay, I'm sharing the screen. Hopefully you can see the screen.
Yep,
So
that's great.
I'm looking forward to this talk. I'm going to talk about predicting unprecedented events. And this sort of the title slide, you see things we know about and there are things unknown that we don't know about. And climate sort of in between. And we're trying to predict something which we may have never experienced in the past. So I work at Texas A&M University, and I'll talk about some of my collaborators as I go along in some of the work. So this is a topical issue because a few days ago, the Wall Street Journal published a very long article about the NCAR climate model. And it talked about scientists encountering limits of computer models bedeviling policy. I talked about supercomputer simulations, complex physics, and the impact of clouds. So there is climate models are getting very complex and they're hitting up against some limits. And so how can we understand this situation? So I just want to go back to a sort of old song. How do you solve a problem like Maria? How do you catch a cloud and pin it down? So we can modify it somewhat. How do you solve a problem like climate change? And how do you catch a cloud? I mean, clouds actually play a big role in the uncertainty surrounding climate change, as you might have seen in the newspaper headline. And ultimately, the problem we face in climate change is how do you predict an unprecedented event? And that leads to some philosophical questions. So I'll try to address them as I go along in this talk. So typically, we're trying to predict something over time. And it's a quantity of interest. It could be temperature, it could be rainfall. So you have some data about how it evolved in the past. So you can plot it and up to the present time, and then you have to predict what's going to happen in the future. So if you the only data you have is this line and a quantity, a scalar quantity, You have a few choices. You can just extrapolate linearly, but if it's not a straight line in the past, you don't know how far back to fit the curve. So you need some kind of a physical model to figure out how far back you should fit the straight line. But the future may not be a straight line. It could curve up, it could be a parabola, it could be exponential, or it could go down. If you're trying to predict El Nino, for example, even if it's going up now, it may be going down sometime in the future if it's an oscillation. So it is very tricky, given limited data, to predict the future. But if you have data from the past for similar events, then you can use that information to predict into the future. But if you don't have data, what do you do? So that's sort of the conundrum we face when we deal with global warming. So here's an answer to the question, how do we predict into the future? And this is a quote I found on Twitter from Carl Wunsch, an MIT oceanographer. So if you want to make a prediction, you better make sure that you're either in sample, that means you have data from the past for the event you're trying to predict, or that you know the differential equation. So if you don't have data from the past, but if you know the differential equation and you have a good estimate of the initial condition, you can put that into your model and predict it. But if it's neither, if you're out of sample and if you don't know the differential equation, you really, really can't predict. So that's sort of the, so we are somewhere in between when it comes to climate change. So that's sort of the theme of this talk. So in terms of modeling philosophy, going back to Wunsch's quote, you can have this empirical approach based on past data, which is in sample, or you can do a physical approach based on the equations of motion, or the equations of radiation. And those are the differential equations. So if you start with weather forecasting, it was an empirical discipline for a long time. There was a famous forecast made for the D-Day landing of the Allies in 1944. And it used a technique called analog forecasting. So the forecaster would simply flip through maps of past weather events, find the one that closely matched today's event, and use that to predict tomorrow's event. So that's called analog forecasting. And that was the only way to do it because there was no scientific way to predict the weather. But in 1950, the first computer was invented, ENIAC. Von Neumann and Jules Charny worked together to make the first weather forecast. And they used the equations of motion, the barotropic vorticity equation, and solved it to make the first forecast. That was the first experimental forecast. Operational numerical forecasting took a decade or so for it to become accepted. But the pendulum of modeling swung from empirical approaches to physical approaches, and modern weather prediction systems are all based on physical approaches. And there's a bit of correction, model output statistics, but the basic approach is based on solving the differential equation. So in principle, you can predict out of sample events. So we'll talk about that. So this is the first part of my talk. How do you predict unprecedented weather events? So we have a huge sample of weather events going back 50, 100 years. 50 years if you want a lot of data, 100 years if you just want surface maps maybe. And so most of the events we predict in weather are in sample, and we know the equations fairly well, especially for motion of dry air. Clouds are a little more complicated, but it's somewhat less important for weather than it is for climate. So in this part, I'm presenting work mostly done by my postdoc, Xue Liu, and also my collaborators, Ping Chang at Texas A&M, Chris Patricola at Iowa State, and Travis O'Brien at Indiana University. And this part of the research was supported by the DOE RGMA program. We're looking at weather extremes in climate models. So I'm going to focus on a particular extreme that happened in June 2021, less than a year ago. It happened in Western North America, in the US and in Canada. It made a lot of news because it was so extreme. I'm going to focus on a region that's shown there that's in the Pacific Northwest in the US and in Western Canada. So if you look at the bottom panel, you see a temperature, maximum temperatures of annual maximum temperatures from 1950. And you can see a slight upward trend, but it's not that much up until 2020. And the green line is a 10-year running mean. So you don't see anything dramatic. You can see the standard deviation of the extremes. But what happened in June 2021 was you got this huge extreme, this like 4 to 5 sigma or 5 standard deviation from the normal. So you got about a 5-degree warmer than usual extreme, and there were severe consequences for human life. And there was a town in British Columbia that actually burned down soon after this heat wave event. So this clearly is out of sample if you think about a statistical sample. And how can we predict these out of sample events? So can we predict it in weather models, and can we predict it in climate models? These extremes. The normal extremes, you see them all the time, but these 3 sigma, 4 sigma, 5 sigma events. A 4 sigma event, for example, would happen about once in 10,000 years. So it's supposed to be very infrequent, but you may start seeing them more frequently as the climate warms. So we're going to use a few data sets in our analysis. We'll use ERA 5 reanalysis for data. Some of the runs would use the NCAR Community Earth System model, and some would use the DOE Energy Exascale Earth System model known as E3SM. We'll use 2 resolution, a low resolution, which is nominal 1 degree in the atmosphere, 100 kilometers by 100 kilometers. It's low for this talk, but it is sort of the standard resolution for climate models still. And we also have some high resolution integrations at 1/4 degree nominal or 25 kilometer horizontal grid. So this is a paper by Fisher et al. In 2021, and this appeared just a few weeks after this big heat wave event in Western North America. And it showed that the CESM model, large ensemble, had a particular ensemble member which showed this temperature anomaly in Central North America. It's a slightly different region, but you had this record-shattering event which is well beyond the 1,000-year return level. So if you look at a large enough sample, you can find extreme events even in climate models. This was an 84-member large ensemble. So if you look at a large enough sample, you can find these extreme events. And even a climate model is able to predict these sort of wacky extremes. So what we're going to do is to look at this particular Western North America event. So here's the same time series again from observations showing maximum temperatures, annual maximum temperatures in the Western North American region. So we're going to look at this simulation first in a control simulation of CESM from 1950, keeping everything at 1950 values. We'll do low res and high res simulations. So what we see is the annual maximum fluctuates, but there's no sort of a very weak trend maybe, but practically no trend, and nothing unusual happens over a 100, 200-year period. And some of the high-res runs were done for the high-res MIP experiment in this. So we can also look at transient runs where we change the greenhouse gas forcing starting from 1950 well into the future to 2050. So if you look at these transient runs on the bottom right, you can see they start showing these extremes. So this is the low-res model in 2018, there was an extreme. These are not 4 to 5 sigma, they're more like 3 to 4 sigma events. So not as extreme as what we see in Western North America case, but still pretty unusual. And if you look at the high res, you can see 2023 simulation had an extreme event. And if you compare it to the control baseline, it is about 4 sigma off. If you compare it to a different baseline for a warmer climate, it's not that far off. So even climate models are capable of capturing these extreme events. This is an interesting topic because when the Western North American event occurred, there was some controversy as to can models actually capture these extremes or are they inadequate? And that is an important issue for something like hurricanes. Climate models don't resolve hurricanes. A 100-kilometer grid isn't going to resolve the eye wall. But these heat waves are driven by large-scale atmospheric weather patterns, high-pressure ridges and blocking patterns, which even a 1-degree model should be able to capture, and the simulation data seems to suggest that they can. So we'll analyze some of the aspects of this of these two extreme events that are in the model CES or model simulations. So if you look at the upper level flow that's associated with these simulated extreme events and compare it to observations, we see quite a bit of similarity. On the left, you see the era 5 for the Western North America event in June. On the right, two are the low res and high res upper level geopotential height patterns corresponding to the extreme event in the model simulation. And you can see a similar blocking omega pattern. It's not exactly the same. We're not comparing the same event. We're just looking at extremes. And you can see the model is capturing upper level geopotential height. And these are large scale patterns which a 1 degree model should capture pretty well. So next, we asked the question, if you run the climate model in a forecast mode rather than a control simulation or a long climate change simulation, can it actually forecast these events well? So we did 1 week forecast using the E3SM atmospheric model initialized with observations. So when we do that, this is the model simulation, it's the forecast of the Western North America event, a 1 week forecast, verified on June 27th. And you can see on the left is observed upper level pattern. In the middle, you can see even the low res model is capturing many aspects of it, but although it's off on the details. We also did 3-day forecast, and when you do a 3-day forecast, it does a whole lot better. And then on the right, you have the high resolution model 1 week forecast. And again, it's capturing the upper level flow pattern better. So if you give the right initial condition to these models can capture these events about a week or 3 days in advance quite well. So they're capturing at least the dry dynamics of this event. But if you look at the actual temperature maximum as forecast by the E3SM model, there are some deficiencies. The black line is observed temperature maximum, and the three dots are the actual local measurements. And the green and blue and the red are the low res and high res simulation. And you can see the forecast overestimates the maximum initially, and then it doesn't persist the heat wave. It falls off too quickly. So what we decided to do was to figure out if there are deficiencies in the model that can be responsible for this. So we decided to do some sensitivity experiments. So we took the initial condition in the model and then modified the moisture by decreasing it or increasing it by 20%. And we also did that with the evaporation coefficient to see how it affects the forecast of the heat wave. Because the climate models do tend to have errors in the moisture budgets. And so what I'm going to show you is the forecast with these perturbations put in the initial moisture or in the evaporation coefficient. So on the top is the picture I showed earlier of the control forecast. At the bottom, you see these additional forecasts with perturbed moisture. And what you see is that perturbing the moisture changes the maximum simulated temperature. And this is the bottom figures for a shorter period than the top one. So it sort of expanded from June 20th to July 2nd. So if you focus on the expanded period, what you see is that the forecasts which have drier initial conditions manage to persist the heat wave as compared to observations. So what this is telling you is that you want to pay a lot of attention to the moisture simulation or the moisture bias in climate models if you want to get the statistics of the heat waves right. Models are pretty good at capturing the dry dynamics, but things like soil moisture can affect the actual simulation of the heat wave. And resolution doesn't seem to matter that much for this particular type of extreme. I mean, obviously, it would matter quite a bit for something like a hurricane. Because we saw earlier that the low res and high res give roughly the same forecast. So the conclusion of this part is that the Western North American heat wave in 2021 was unprecedented in magnitude, but not so much in mechanism. So the models captured the mechanism pretty well. And so differential equations are able to capture the unprecedented magnitude of this event. Technically, it's out of sample, but we know the differential equations. That's why we could predict it. And even coarse models do a pretty good job of this type of extreme Although for hurricanes and intense rainfall events, you really want perhaps a high resolution model. And if you're trying to improve models, you probably want to pay a lot of attention to the moisture bias. And that was the goal of the DOE project, to try and see how the biases in the climate models can affect simulations of extremes. And in other cases of unprecedented events, I live in Texas, and Hurricane Harvey was an example of an unprecedented rainfall event. We had about 50 inches of rainfall over 5 days, which is like annual rainfall in 5 days. The models actually predicted that quite well, even though it's unprecedented in the data set. So for the first part of this talk, knowing the differential equation helped us predict unprecedented events quite well. And now I'm going to shift gears and look at a slightly different problem. So in climate, we'll argue that climate change is going to be out of sample. So that's going to create a problem right away. And we know the equations less well because we're going away from motion of air into motion of ocean water, and also things like vegetation and carbon cycle. There we know the differential equations less well. So what I'm going to do here is to interpret the latest IPCC report, the AR6, which came out in August, using some of the ideas from my book about the philosophical aspects of climate modeling. The book was actually written before the IPCC report, so it doesn't actually talk about the IPCC report. But some of the ideas from the book directly apply to the IPCC report. And there's some surprising things about this particular AR6 report as compared to the previous ones. So going back to predicting something into the future. So here what we're trying to do is to predict the temperature of the globe, knowing what we have until present and trying to extrapolate it into the future. Again, it's not always a linear trend. It could go up, it could go down. There's also the human factor that comes in, but let's discard the human factor now. But for a given scenario of emissions, how is the temperature going to change? So on the left is the famous Keeling curve that shows carbon dioxide concentrations over time. And we know from models that the increase in carbon dioxide concentrations is driving the global warming. So the question is this unprecedented? So if we look at past data, what appeared at the bottom is carbon dioxide concentration from ice cores. That's on the black line on top in the bottom figure. Below that is the temperature change in a gray curve, again measured from ice cores. And the dashed line that looks vertical right at the end, that is the Keeling curve. So by geologic timescales, the climate change we have is extremely, extremely rapid. So the pace of the climate change is unprecedented. And that it's important because climate feedbacks can be fast or slow. So geologic climate change often involves slow feedbacks like absorption of carbon by rocks, which operates at a 1,000-year timescale, which is not going to be operational now. So looking at this curve, we can see that climate change that we see today is basically out of sample. If you go back further in time, millions of years, there are cases where carbon dioxide was driving climate change. But again, that happened over thousands or tens of thousands of years at the fastest. The other aspect is a lot of climate change in the past was driven by orbital forcings, whereas climate change today is being driven by something completely different. That's the emission of carbon dioxide very quickly by fossil fuel burning. The other aspect in the past is that if you go back millions of years, the shapes of the continents were different and the sea surface temperature patterns were different. And we know from studies that how the globe warms depends on the surface patterns of warming. Warming in the tropics excites clouds in a different way from warming in the exotropics or in the polar regions. So all that needs to be taken into account if you're going to look at the past to learn about future climate. And it gets hard because the sample is pretty limited. And past data doesn't actually measure temperatures, so we rely on proxies to estimate temperature using pollen or tree rings or isotopes in air bubbles. So how do we predict climate? So we have a very complex system, which has atmosphere, ocean, land, sea ice, all of them interacting. And so the approach we use philosophically is called reductionism, where we take a complex system and reduce it to a collection of smaller interacting subsystems and study each of these subsystems separately. So it's like if you look at a watch, it looks smooth and nice on the face. But if you open it up, you can see a very intricate mechanism. And you want to try and replicate all the intricate details of the interactions in climate to be able to simulate its future. So again, we want to simulate the globe. We divide it into grid boxes, and we try to solve the differential equation on the grid boxes. But things like clouds are too small for the grid boxes, so we make approximate formulas for them and then try to solve that. So we reduce a complex problem into simpler and simpler components. And the earliest climate models were very simple. They had only a few thousand lines of code, and they represented something like convection very simply by like a radiative convective model, for example. So one of the quantities I've been talking about is climate sensitivity, which is defined as the warming of global surface temperatures if the carbon dioxide is doubled. So typically it's done by instantaneously changing carbon dioxide concentrations and seeing how the globe responds. This is a simple metric because it doesn't depend on ocean heat transport, because it talks about equilibrium and the ocean transport has equilibrated. And it doesn't depend on a particular scenario for a future emission. So this is often used to compare the performance of different models to see whether one is predicting more warming in the future as compared to the other. So we'll use this metric to compare climate models as they've changed over time. So returning to the philosophical approach, in the weather case, we went from empirical approaches to physical approaches in 1950 with von Neumann and Charney. So climate modeling also had a physical approach, 3D global, starting in the 1960s and 70s. And what you see here is a picture of Suki Manabe and Jim Hansen, who sort of pioneers in the modeling the climate sensitivity. And in 1979, Jules Charney chaired a committee that produced a report providing the first estimates of climate sensitivity. And since from 1979 to 2013, that's the fifth assessment of IPCC, the physical approach to estimating climate sensitivity dominated. And that's a reductionist approach. And Suki Manabe actually won the Nobel Prize in physics in 2021 in recognition of his pioneering efforts in the 60s and the 70s. So now we'll see how this pendulum of modeling philosophy has changed in the rest of this talk. So climate change is an unprecedented threat, and this is a quote from Donald Rumsfeld, which is often used in dealing with unprecedented threats. So he talks about known knowns, things we know about. In the climate context, it'll be differential equations that describe the motion of fluids. We can solve them on a grid and do a good weather forecast, for example. There are known unknowns, things like boundary layer bulk formulas, where you have the formula, but the coefficient is unknown, the parameter is unknown, but can adjust it, and then we can solve the prediction problem. And also there's unknown unknowns. A good example of that was in the ozone hole case. There were polar stratospheric clouds and heterogeneous chemistry on surfaces, which is completely unknown. But once people knew it, they could deal with it. But there are things we don't know about, which we'll discover as we do more observations of this nature. So what we can do is use Rumsfeld's phrases to construct a matrix. We have known knowns, known unknowns, and unknown unknowns. On the y-axis, you have awareness of a threat. So as you start knowing things, you get more aware of it. On the x-axis, you have accuracy with which you can represent that threat. So initially, you become aware of something, and then you start to build a model of something, and the model gets better and it gets more accurate. So this two-dimensional matrix sort of defines how we build models. So climate is a complex system, and it spans the known unknowns and the known knowns. What we do is model improvement. As we encounter a new process, it could be polar stratospheric clouds, it could be just tropical clouds or cirrus ice crystals. We build parameters, we'll build formulas to parameterize it. And when the models get more sophisticated, we can actually resolve it. An example where we went from parameterizing to resolving is ocean eddies. In earlier climate models, ocean eddies were parameterized for the heat transport. But in a quarter-degree atmospheric model coupled to a tenth of a degree ocean model, we can actually resolve the ocean eddies. So the ocean eddies are moved from being known unknowns to sort of known knowns because we can resolve them on the grid of the model. So model improvement goes along this arc. But calling everything that's parameterized as known unknowns is sort of too broad. So what we can do is to define two different categories. We have well-known unknowns and poorly known unknowns. So by well-known unknowns, I mean something like a bulk parameterization where we know the formula, but we don't know some of the coefficients. So we can tweak the coefficient, adjust it, and do a stochastic estimate of the uncertainty. But we also have things like clouds or effect of aerosols on clouds where we don't even know the formulas. People propose different formulas. So the structure of the formulas themselves is unknown, and that is much harder to deal with. So you have structural uncertainty in models. So parametric uncertainty can be dealt with by exploring parameter space, but structural uncertainty, you could have different formulas. You could have quadratic formula, you can have exponential formula, you can have different terms in your formula. You can have a statistical approach, a physical approach. So it's a very hard problem to deal with. And then of course you have unknown unknowns, but those we know nothing about yet. So the question I was addressing in my book is, if we keep doing the reductionist approach, getting more and more complex models of smaller pieces of the mechanism, is there a limit? So that's sort of a philosophical question. And here's an example of a schematic of a climate model, an Earth system model, and you can see how complex it is. There are different components: atmosphere, inland ice, vegetation. The atmosphere has dynamics, thermodynamics, chemistry, and clouds. So this is a paper. This is from a paper by Easterbrook and Johns, and they looked at how complexity of code has changed over time in a particular model. This is the Hadley Center unified model over a 15-year period. On the x-axis is time, on the y-axis is the lines of code, and the green curve is the lines of code, and the blue one is the number of files in thousands. So lines of code in thousands, the number of files in thousands. So in 15 years, the lines of code went from 100,000 to 1 million. And the number of files sort of increased more slowly. That's interesting because basically the files are getting larger as the code is getting larger too. But basically, you have a tenfold increase in complexity of the model by this measure in a 15-year period. So it's pretty amazing, the amount of complexity. So I'm going to step back now to weather forecasting. When you start improving the resolution of a model, you expect the results to converge. Like if you're designing flow over a wing, design an aircraft, as you get to finer and finer grid to do a computational fluid dynamics simulation, the results converge, and then you get to design a wing based on a converged result. So do we see convergence in climate? So before we get to climate, I want to talk about weather convergence. And this is from the ECMWF model. And this is anomaly correlation scale measured in percent for a 3-day forecast. On the top curve is Northern Hemisphere scale, and the bottom curve is the Southern Hemisphere scale. And in the early 1980s, there was a big spread between them because there wasn't much data in the Southern Hemisphere. And the data assimilation schemes were primitive. There wasn't much satellite data. But over time, both Northern and Southern Hemisphere skills have improved, and they've converged. And what you see is that the asymptotic, it's not going to get to 100% because you're facing a predictability limit, that's the Lorentz limit of about 2 weeks. And if you plotted the same curve for a 5-day forecast or a 7-day forecast, they'll asymptote at lower levels of skill. So you get convergence and asymptotic convergence, and the Northern and Southern Hemisphere are converged together because as model resolution improved and data assimilation techniques have improved, you're able to solve the differential equations better, and that's giving you convergence. So we're seeing convergence in weather forecasting just as you see in a computational fluid dynamics model. But let's look at climate prediction. So the bottom panel shows the range of climate sensitivity assessed over a long time period. We start with 1979, and The Charney report assessed the climate sensitivity as being between about 1.5 and 4.5. So that was 1.5. They used Suki Manabe's model and Jim Hansen's model. They had two different numbers. They just used those as a model spread and came up with a mean estimate of about 3. So that's in the middle of this bar. So that's the first scientific estimate of climate sensitivity. The first IPCC report also used models, that's the red. And then IPCC takes the models, but then uses other data like observational data to come up with its own assessment of the spread of climate sensitivity, and that's the green bars. Again, the green bars are fairly close to what the models estimate because the models dominated the assessment. That's the AR1 of IPCC in 1990. And then we have IPCC AR2. Again, the model spread fluctuated. The assessment also changed. Actually, the assessment didn't change at all. We have AR3, model spread widened again. Assessment didn't change. And then we have AR4, the model spread got narrower. Assessment actually got a bit narrower. We have AR5, the model spread got wider and the assessment got wider. So IPCC assessment of the model spread have been fluctuating, but not by very much. But the mean climate sensitivity has roughly been about 3 Celsius for doubling of carbon dioxide over this entire period. So what happens now with the latest IPCC? This is from CMIP6, the climate model intercomparison for the latest IPCC. And what you see is the model spread actually has gotten wider. It's the widest it's ever been. And we have models with climate sensitivity exceeding, 5.5, which is very high. And it's also gone up. Even the lower end has dropped a bit. So the model spread actually got wider with the latest generation of CMIP6. What about IPCC assessed spread? It's actually gotten really, really narrow. So the model spread's gotten wider and the models have not converged as they've gotten more complex. But IPCC has assessed its the narrowest assessment of climate sensitivity so far. In a moment, I'll explain what is the basis for that. But what this suggests is that the model spread isn't reducing as the models have gotten better. So increasing complexity is not giving you reduced uncertainty in global metrics like climate sensitivity. The models are better in regional climate. They can probably simulate tropical cyclones better, but that's not adding up to reduced uncertainty in global estimates like metrics like this. In this particular case, remember the NCAR headline about climate models facing limits? The NCAR model produced a very large climate sensitivity, and they traced it back to how clouds were parameterized in the model. And many of the high sensitivity models have issues with the cloud parameterization. There are a lot more coefficients to tweak, and some of them tweaked in a way that gave high sensitivity. So increasing complexity is not giving you reduced global uncertainty. But those models do perform better in many regional metrics, and they get better budgets for many, many things. So it's sort of a mixed bag. Why did IPCC assess a narrower range? So IPCC uses many empirical estimates. It uses something called process understanding. And what you see in the x-axis is the climate sensitivity here. And the y-axis is the different metrics that the IPCC uses. So it uses process understanding, the instrumental record, paleoclimates, emergent constraints, and combines them all. It combined them all to come up with the latest assessment. The black line is the narrow assessment. And the bottom row is the models, and the blue axis, you can see it's a very large spread. And you have these very high sensitivity models, even exceeding 5.5 for a few models. So the IPCC no longer relies on models as the primary driver of the assessed sensitivity, and it's relying more on something like emergent constraints or paleoclimate or the instrumental record to make this assessment. So there's been a pretty big shift in the philosophy of how IPCC does its assessment. And this also affects its assessments of global climate change. So this is from AR6 report, and this shows the IPCC assessment of global surface air temperature for 80 years from now. And what you see is at the x-axis of different scenarios, starting with the low emission scenario, SSP 1.9, all the way to SSP 8.5, the high emission scenario. And you see two bars for each case. The gray one is the CMIC 6 models, but what the IPCC did was it didn't use the widespread of models. It took, basically it weighted models differently based on how they simulated recent warming. So if the models did the recent warming, simulated the recent warming too high for the period between about 1984 to 2004, for about 20-year period. If the model simulated too much warming in that period, they picked that period because that's when the global warming signal stands out from the background noise. So the models were too warm, they were weighted less. And by doing that, it was able to constrain the warming, and it actually the constrained model's projection looked more like CMIP 5. So that's the gray bars. And then it used very simple energy balance models and used its assessment of climate sensitivity based on data to come up with the green bars. And it combined them, it averaged them to produce estimates of global surface air temperature in the next 80 years. So this is quite different from using just climate models to predict the future. But you can only do this for the global mean. You can't do it regionally. And IPCC had a different way of doing it regionally using something called global warming levels. So in some sense, IPCC is using climate models to downscale global mean temperature, which is sort of a radical shift if you think about it. So back to the philosophy pendulum, as I said, between 1960s to 2013, relied on a physical approach, a reductionist approach to predict future climate. But now you shifted not all the way, but more towards the empirical approach for predicting climate. And what you see on the left at the bottom is IPCC AR6. And the probability distribution is the one from something called the WCRP assessment that came out in 2020 that used data to estimate climate sensitivity. And those are the different estimates. So that sort of is a main player in driving the narrower IPCC AR6 assessment. So we're seeing the pendulum moving back towards the empirical approach. And there's some interesting trends. One of the hot topics in climate modeling is machine learning. And that is, if you think about it, it's a very empirical approach. It depends on being in sample. And it's still an open area of research, but if it succeeds, it's going to be pulling prediction towards more an empirical direction. So that's an interesting thing to watch out for. So I'm going to conclude in a moment. So coming back to the headline I started with, so we are encountering models in climate models, limits, and we're facing limits in complexity. And the question is, making parameterization better, like cloud parameterization better or more complex, is it going to help us reduce uncertainty? Or we need to step back and decide maybe it's too complex. So I don't know the answer to that question, but complexity is not reducing the global uncertainty, but you still need better representation of mountains. You need a better grid. There's still processes that are not in models, so you probably want to put them. But what is the balance between complexity and importance of processes? And if the IPCC is moving more towards an empirical approach to predict future warming, what is the important role of models? So that's a very, very interesting question to think about. So here are my final thoughts. So we try to predict two different kinds of unprecedented things. We try to predict unprecedented weather extremes or extreme extremes. We know the differential equations, and we can actually predict those fairly well. And especially with dry dynamics, we can resolve it on the grid. Something like hurricanes, intense precipitation, how it's going to increase in the future, that's going to be harder. We may need cloud resolving models to attack that problem. But as model complexity continues to increase, it's a mixed bag. More grid points are definitely going to help you predict hurricanes better. If you're living near a mountain, you probably want a better model, a high resolution model to predict the difference in rainfall on the two sides of the mountain. But just increasing parameterization complexity may yield diminishing returns. So we may need to step back and think about that. And climate sensitivity is not converging like you'd expect for a typical computational fluid dynamics problem. It's not computational fluid dynamics. You have equation for the fluid, equations for carbon cycle, and now people are putting equation for the land ice sheet. Putting in additional equations introduces additional parameters, and that is not really going to help convergence. So we can expect more regional detail, but maybe not less global uncertainty. Thank you.
Thank you. That was a great talk. But we will have a Q&A section, but before we do that, I just want to announce the winner of our giveaway. So I'm just going to say it. Usually, so the winner is Aning Cheng. Please forgive me if I have pronounced your name incorrectly. Aning, if you want, you can turn your mic on. Otherwise, I will use the email on your entry, and we'll contact you, connect you with the publisher, make sure you get your book. Cool. Okay. It's Q&A time. If anyone has any questions, they can. Oh, I see Sumant has his hand raised. Sumant, you can go ahead and unmute yourself and ask the first question.
Hi, Saravanan. Good to see you and a nice talk. You raised very important questions, and my comment is the weather prediction models are also complex, perhaps not as complex as climate models, given that we have to consider several systems in the climate model. But even so, the fact that the weather models are converging and doing better or than the climate model raises an important question. And the way I see it is the weather models are performing so well or almost at the limit, so to say, because they've been tested every day. We make a forecast every day. We have been doing that for decades, learning from our forecast errors, correcting the model physics, and doing these things. With climate models, we have never really taken them through the paces as we have done with the weather models. We have not gone back and predicted the dust bowls or the pluvials or the hiatus from warming, which all models should be doing for the historical climate. And I think that's the process which helps us, I think, improve model physics and inter-system exchanges and such, and improve the climate models. So I think part of what you suggested is true, and also that we haven't really flexed the climate models to the extent we have done with the weather models.
Yeah, hi, Samantha. Good to see you. Yeah, I agree with you. One of the challenges, I guess, we face, I mean, I work with the NCAR model, for example, that there's always this pressure to run the most expensive model, so we can't do enough sensitivity studies. For example, when they ran the NCAR model for the last glacial maximum, they got a huge climate sensitivity of huge cooling of, I think, like -10 degrees, which is very, very unrealistic. So as you said, it's very good to test the models in many, many different ways. But if you're running the highest resolution model, you barely do 3-member ensemble, and then you're done with the IPCC. So I think there needs to be sort of a very large exploration of different parameter regimes, as you say, and not just focus on the latest and greatest high-res model with many zillions of parameter additions. So we may need to slow down how quickly we move in that direction. I agree with you.
Couldn't agree more with you. In fact, I think the IPCC deadlines has hurt science because all the centers are trying to make their models more complex and trying to gear up for the next IPCC run rather than spending the time more judiciously vetting out the climate models. So I'll stop there.
We have another question from Mike Evans. Mike, you can unmute yourself.
Yeah, thank you. What do you think are the prospects for a climate model that's kind of scale agnostic in time and space, meaning it's as good for climate prediction over even paleoclimatological timescales, all the way out to weather timescales?
Well, Well, it's a practical, I mean, it's a scientific aspect of it and the practical aspect of it. The weather models today run at about 10-kilometer grids, and climate models, as I said, the state of the art is between 50 to 100-kilometer horizontal grid. We had access to some 25-kilometer grids, but that's sort of the bleeding edge. In a few years, it will probably become state of the art. But the interesting thing is, climate model grid has stayed around 100 kilometers for the last few iterations of the IPCC because the extra computing power is going into extra processes. It's very interesting that if you can put in like 100 species of chemistry, the chemist would be very happy to do that. There's always a tension. And so it's, people develop paleoclimate models running at coarser resolution because you need to run thousands of years. So for a practical reason, any model that works for the last glacial maximum is going to be a much coarser grid model with probably fewer parameterizations. But as I said, maybe you can still learn a lot from that model. But for practical, you can have the same code base, but the resolution and the parameterization will be different. And that makes the parameterization different because if you change the vertical resolution, you have to change the radiation parameterization, for example. So you can have the same code base from a software viewpoint. I think that was the goal of the Hadley Center unified model. The word unified there says it's the same model, code base, but the actual configuration is going to be different. I don't see a way we can run a 10-kilometer model, paleoclimate timescales. Again, a related question is scale-aware parameterization. That people, it's one of the hot topics. Can you have parameterization of cloud that smooth, gradually goes from 3 kilometers to 25 kilometers when you resolve clouds to parameterize clouds without creating a discontinuity? So that's a scientific challenge as well.
Thank you.
Thank you. We can have another question. Oh, Sumant, you can go ahead and unmute.
So the example that you started out with was a great one. This warming in late June last year, it was very intense. And I'm sure if such an extreme event had happened in winter, it would have been more amenable to analyses because we know many of the relevant subseasonal teleconnection patterns. And the question there would be, can you see a negative phase of the PNA in association with the North Pacific Oscillation or something? In other words, interesting pairing of winter teleconnections. Because we know those very well, I'm pretty sure that an extreme event in winter would have gotten much more, we would have more insights on that by now. But because that happened in summer, a season for which teleconnection patterns are not well defined or well characterized, I think it remained an enigma till the end. Any thoughts on?
Yeah, I mean, I don't have much to add to what you said. The way I just think of it as it's basically a blocking pattern.
Mm-hmm.
And the question is, I mean, this question of whether it's forced variability or internal variability. Our experiment didn't address that. We didn't even address the attribution issue. I'm sure that people studying whether climate change, how much climate change is responsible for that. That requires a different suite of experiments. All we did was to show that models can get something like that, and that moisture could play a big role. But yeah, it's an interesting question whether some kind of a sea surface temperature pattern in the Pacific affected the probability of this event occurring.
Thank you.
Great, we have time for some more questions. You can raise your hand, or I should say, if you don't have a microphone, you could just type it in the chat and I will read it out loud.
At risk of this being like the Sumant and Mike question festival, could I just pick up on Sumant's question about that simulation experiment you ran? I was expecting you to say that it was increased moisture that created the persistence, but it in fact was reduced moisture, if I understood correctly. Could you explain a bit more about that?
Yeah, actually, I thought increased moisture would make it worse. Yes, it just seems to be that moisture. Again, I think if you look at the climate viewpoint, you probably get a different answer. But there's a particular event where moisture is probably coming from a particular direction. So I'm not sure. My intuition was that, yeah, moisture would make heat waves worse. That's what you expect. In terms of bearability of heat waves, a moist situation, it's hard to bear a heat wave. But in this case, I guess if it's dry, it just warms up more when the sun heats things. So that's the way I explain it. But it may be very case specific here. Very case specific here. It could be assimilating one event, not all heat waves of that type.
Any other questions or comments? Okay, unless someone interrupts me here, I think we could probably wrap up the seminar. Thank you so much to our speaker. This was a great talk. Congratulations to our winner of the giveaway as well. I'll be in contact. And to everyone else, please come back next week as our seminar series. Oh, it's on Tuesday though. It's on Tuesday because Monday's a holiday. So thank you, everybody. Have a great week.
Thank you.